Okay, hello everybody. So this is about linear approximation. Arguably the best way to think about derivatives. Certainly extremely useful. We will use this to solve chemical reaction networks, to track the motion of planets, and to do machine learning. We will do all of this by linear approximation. So very important. Okay, so Part A, give the formulas for linear approximation of some map that I didn't tell you its explicit formula. And then Part B will do something with an explicit formula of a map. So Part A, just what are the formulas for linear approximation? Here is my answer. So this would get, for full credit, it has actually words, formulas, and cartoon pictures of the input and output space. So the input point x in the input space, Rn, gets mapped to an output called f of x usually, right? And a nearby point, x plus a little bit of movement, v, so a nearby point x plus v, over here we move from x to the point x plus v, and there's the little vector v that's moving us. For some v, gets mapped somewhere else, okay? So a nearby point gets mapped somewhere else, not very surprising. We call it f of x plus v, f of that point. The formula is that we can get that point approximately, the output, we can get that output approximately by if we know the input at x, and if we add the derivative in the direction that we moved. So in other words, take the output from the start point, which we might know in physical problems. We'll know how many chemicals we pour in at time t equals 0. So we know the output at the start point. And then we move in the direction that the derivative tells us applied to that movement vector. So if we move a little bit, then we should move the output by the derivative. And so that moves from the f of x to this point, which is our approximation. Now, secretly, the actual value might be somewhere else. But the whole point here is that oftentimes we cannot find this next value because it's too complicated. So it's good enough to be almost there. And so that's what we use the derivative for. Okay? All right, so that's my answer to A. What about B? Explain further by approximating this specific map. This is a map from R2 to R. So it assigns a real number to every point in the plane, like maybe the temperature of the world at that point. And approximate it near the point 2, 1. Okay. So here's my answer. There's a lot of choice here because I just said approximate it near the point 2, 1. Now what I chose to move that way. You could choose a different vector. So I chose to move in the direction -3, 1. So that would be this very long vector. But then my approximation is going to be bad. It's really good for short movements. So what I did is I took that vector and I shrunk it down to 1/10 the size. And here's that little vector that I pictured. So now that's where I'm going to move. You could move somewhere else. Okay. And so in this case, then x plus v for this v I chose is, okay, well, maybe let's start from the beginning. So here's the map. I just copied it down from the problem. Right away, I can compute the derivative in the first dimension by just differentiating this with respect to x1, and I get 2x1 minus 0, because this part doesn't depend on x1, so its derivative with respect to x1 is 0. So that's how I get this. And then at the point x equals 2, 1, this x1 becomes a 2, and I get a 4. So that's the derivative at this point. The other derivative in the second dimension, I take derivative with respect to x2, and I get a minus 2x2. from single variable calculus. We know that, minus 2x2. Now I plug in at the point it told me to use in the problem, 2 comma 1. Well, that means that I plug in a 1 and I get a minus 2. Okay? And then down here is where I use that 4, where I use that minus 2. And I think I made a mistake, actually. Yes, I did. Okay, so let's look at the mistake I made. When I plugged in here, I plugged in V, and I put the 1.7 and 1.1. That's there and there. That's extremely wrong. My V was up here. This was V. And so I should have put not a 1.7 there, but actually this should have been, what is it? This should be negative 0.3 times 4 plus. And now not a 1.1, but rather a 0.1 times negative 2. And so that would have given me a negative 1.2 plus negative 0.2. Okay, and that would give me negative 1.4 in total. So that's what I would do. This part should be actually, it shouldn't be 3.08, it should be negative 1.4. And so my f of x was just when I plug in the 0.21, I get 2 squared minus 1 squared, which is 3. And so that's why I have a 3 there for f of x. And then I need to update it by the derivative, which I should apply to v, not to x plus v. So yeah, I made a mistake. So this is not right, this is not right, this is right. And so I should do 3 minus 1.4, which is 1.6. Okay, and that should be my answer. So now I approximated f at 1.7, 1.1, so that's correct. This is the point x plus v, which is right there where I want to approximate f. And by linearizing it, x equals 2 minus 2 comma 1, which is nearby. And the value of, so maybe I'll even write, I approximated f at here by linearizing and obtained f at 1.7 comma 1.1 is approximately 1.6. Okay. And we could check, I mean, we can plug in and actually compute. In this case, we actually can compute f, unlike chemical reaction networks and planetary motion and things in the future, and machine learning updates. So we can square this and subtract the square of this and see if it's close to 1.6. So 1.7 squared minus 1.1 squared. And so let's do this. Okay. You should really use a calculator so you don't make even more mistakes. 2711, and then a 7, a 1, and I add, and then maybe it's a 2.89. Okay, and what's 1.1 squared? 1, 1, 0, 1, 1, 1, 2, 1. Oh, that's Pascal's triangle row. And it's a 1.21. And now I subtract, and if I subtract them, I should get roughly 1.6. Well, what do I get? 2 minus 1 is 1. 8 minus 2 is 6. 9 minus 1 is 8. Is that right? Yeah, and that's roughly 1.6. So, you know, in this case, we could literally compute this function. But in machine learning and other areas, we won't be able to really compute the function. We might not even know a formula for the function. We might not know a formula for the curve which represents the evolution of our chemical reaction network in the 8-dimensional space of the 8 chemicals. We won't know a formula, but we can use this method, and we'll basically be right. Okay. Then part C, I am deleting from the problem. because the problem is long enough. That's all.